Now I'd like to move on to the next issue, which is how to draw the correct stereochemistry for an SN2 reaction. So here's some rules that will help us with that. First rule, here's the rule that we will be using. When a nucleophile attacks an electrophile that is attached to a leaving group, the nucleophile attacks from the side that is opposite to the leaving group. I'm not going to try to explain why this rule makes sense. You might find an explanation for this in your textbook or lecture notes, but for our purposes, we will just memorize that a nucleophile attacks from the side opposite to the leaving group. Well, let's go ahead and see if we can apply that to draw the correct stereochemistry for an SN2 reaction. Please pause the video and try to apply this rule to complete this problem. Well, now we'll go through this together. We should start by numbering our carbons. Now we want to identify roles. Well, we start by focusing on the atom with the formal charge. This negative formal charge makes the iodide want to donate negative electrons, which makes the iodide a good nucleophile. This carbon 2 has a delta positive charge because it's attached to the chlorine. That makes carbon 2 into a good electrophile. And we have memorized that neutral chlorine is a good leaving group. Notice that I'm always careful to articulate what the clue is that tells me why each atom is playing each role. It's good to go through that for each problem to build your skills with these roles. Now we draw the electron pushing arrows. Remember, the arrows should begin at the nucleophile because that's the electron donor. Then the electrons are going to be moving towards carbon 2, which is the electrophile. So we've shown the nucleophile attacking the alpha carbon. Remember that carbon 2 is called the alpha carbon because it's attached to the leaving group. And then here's the arrow that shows the leaving group leaving the alpha carbon. Only after we finish both arrows should we start trying to draw the products. Now this is an arrow that tells us to draw a bond between carbon 2 and the iodide. Notice that we're not going to draw the bond between the iodide and carbon 1, 3, or 4. The arrow makes it clear that we're drawing the bond between the iodide and carbon 2. But notice that carbon 2 is a stereocenter. That means that the geometry, the way we draw this geometry matters for getting full credit. We have to draw the geometry correctly using wedges and dashes. So should we show this iodide on a wedge or on a dash? Well, notice that we have a case here where a nucleophile is attacking the electrophile that's attached to a leaving group. So the nucleophile has to attack from the side opposite the leaving group. Well, the leaving group here is on the dash, which you should know means behind the page. The chlorine is behind the page. So in order to attack from the opposite side, the nucleophile has to attack from in front of the page. And since the nucleophile is attacking from in front of the page, it will end up on a wedge. You should know that a dash indicates a substituent behind the page, and a wedge indicates a substituent that's in front of the page. So we used this rule. The iodide had to attack from the side opposite to the leaving group. The leaving group was behind the page, so the iodide attacked from in front of the page. So the iodide ended up in the position in front of the page, which is drawn on a wedge. I should already have put in some numbers here, numbering consistently with the starting material. Because the iodide is at the beginning of the arrows, we change its charge. It started negative and it lost electrons, so it became one step less negative and became neutral. So that's the way to draw this stereochemistry. The big new issue that I wanted to go through for this problem is the stereochemistry for SN2. So this dash turns into a wedge when the iodide attacks from the side opposite to where the leaving group was. With this arrow tells us to break the bond between carbon 2 and the chlorine. I've actually already done that. And that arrow also tells us to change the charge on the chlorine. Since the chlorine is at the end of the series of arrows, the chlorine started neutral and it's gaining electrons, so the chlorine should become one step more negative and ends up with a negative formal charge. Well, our goal here was to learn how to draw the correct stereochemistry for an SN2 reaction. So we've learned this rule. When the alpha carbon is a stereocenter, then an SN2 reaction produces one product with inversion of configuration. So here's our one product with inversion of configuration. Do you see why it's natural to call this an inversion of configuration? Because we're inverting from the chlorine being on a dash to the iodide being on a wedge. By the way, when I say that there's one product, what I mean is that we only get this product. We don't also get this. We don't get this. We don't get these two products. We just get one product. Of course, in another sense, there's two products if you also count the chloride. But actually, the chloride is not too interesting to us here. Usually the only product that we're interested in is this one. So maybe I should say there's one main product. This is the one thing. We're not too interested in the chloride, so we're saying that there's one main product in the sense that we only get this version of the main product. We don't get another version where the iodide is on a dash. We don't get that for this reaction. So the SN2 produces one main product if we don't count this less interesting product from the leaving group. I hope that makes sense. And again, the idea to memorize is that SN2 gives inversion of configuration, and that's because the nucleophile attacks from the side opposite to where the leaving group was. By the way, I've been using this term stereocenter. I hope you know what the term stereocenter means. A stereocenter is a carbon that's attached to four different groups. So do you see why we would say that carbon 2 is a stereocenter? It's attached to four different groups. What are the four different groups? It's attached to a chlorine and also to a hidden hydrogen, a chlorine and a hidden hydrogen, and also to two different carbon chains. Do you see how these carbon chains are different? There's this carbon chain on this side only has one carbon, and the carbon chain on the other side has two carbons. So those are considered two different groups because these two different carbon chains have different numbers of carbons. And of course, carbon 2 is still a stereocenter in the product. Now the four different groups it's attached to are the iodide, the hidden hydrogen, the methyl group on the left, and the ethyl group on the right. Notice that we only care about stereochemistry for an SN2 reaction when the alpha carbon is a stereocenter. That's why we didn't have to worry about stereochemistry for the previous problems. I didn't have to worry about stereochemistry for this problem because carbon 3 here is not a stereocenter. Carbon 3 was not a stereocenter because it's attached, two of the things it's attached to are identical, two identical hidden hydrogens. Because carbon 3 is attached to two identical hidden hydrogens, carbon 3 was not a stereocenter in this problem, and therefore stereochemistry was not relevant for this problem. For the same reason, stereochemistry was not relevant for this problem, because carbon 2 was not a stereocenter. So stereochemistry is only relevant for SN2 when the alpha carbon is a stereocenter. Let's get more practice with SN2 stereochemistry. Please pause the video and try this problem. We'll start by putting in some numbers. By the way, keep in mind that we're not trying to write IUPAC numbers here. I'm not trying to write down the numbers that would be correct for the official IUPAC naming system. I'm just writing down numbers for my own personal use. So I don't need to worry about whether I should start numbering from the left or from the right. I can start numbering from either direction. Because the numbers are just for my own personal use on this problem, not for official IUPAC naming. Let's identify roles. The negative charge tells us that the bromine will be the nucleophile. Carbon 3 has a delta positive charge because it's attached to the chlorine, and the delta positive tells us that carbon 3 will be the electrophile. The chlorine, a neutral chlorine we've memorized, is a good leaving group. Then we can draw the arrows. So the arrow should go away from the negative charge towards the electrophile, which is also our alpha carbon, and the leaving group leaves in the same step. Now we draw the product. This arrow tells us to draw a bond between bromine and carbon 3. Let's go ahead and put in the numbers right away. Now, carbon-3 is a stereocenter. Carbon-3 is a stereocenter because it's attached to 4 different groups: a chlorine, a hidden hydrogen, a methyl on one side, and an ethyl group on the other. So stereochemistry does matter here, so let's get the geometry here correct. Well, we know that the bromine will attack from the side opposite to the leaving group. This leaving group is in front of the page on a wedge, so the bromine will attack from the opposite direction. The bromine will attack from the opposite direction, which puts it on a dash behind the page. I'll also change the charge on the bromine from negative to neutral. This arrow tells us to break the bond between the chlorine and carbon-3, and that arrow also tells us to change the charge on the chlorine from neutral to negative. So we applied these ideas. Since the nucleophile is attacking an electrophile that's attached to a leaving group, the nucleophile attacks from the side opposite to the leaving group. The leaving group was in front of the page on a wedge, so the nucleophile attacked from the opposite side behind the page and ended up on a dash. And the result of this rule is that the stereochemistry for an SN2 is that the SN2 produces one main product, if we don't count this one, with inversion of configuration. Here we inverted from the chlorine on a wedge to the bromine on a dash. By the way, I think we'll get a better understanding of what inversion means if we also think about the hidden hydrogen on carbon-3. In fact, let's not treat it as a hidden hydrogen anymore. Let's draw in the hydrogen. Let's draw the hydrogen on carbon-3. In fact, you might want to try that yourself. Try drawing the hydrogen on carbon-3 and the starting material and the product. Well, did you realize that the hydrogen has to start on a dash? Since the chlorine was on a wedge, the hydrogen here will start on a dash. This type of carbon with 4 single bonds should have a tetrahedral geometry. A carbon with 4 single bonds has tetrahedral geometry, and the way to draw tetrahedral geometry is 2 solid bonds, 1 wedge, and 1 dash. So you can't draw this hydrogen on a solid line. You cannot draw this hydrogen on a solid line. That would not be the correct way to draw the tetrahedral geometry. We have to draw that hydrogen on a dash. So can you see what happened to the hydrogen in the product? Can you draw the hydrogen in the product? Well, remember that this bromine is attacking from the side opposite to the leaving group. The bromine is attacking from the side opposite to the chlorine. The chlorine is in front of the page. So the bromine is attacking from behind the page. The bromine is attacking from behind the page, and what happens then is as the bromine attacks from behind the page, it pushes the hydrogen out of the way. It pushes the hydrogen in front of the page. As the bromine attacks from behind the page, ending up on a dash, in order to make room, it has to push the hydrogen in front of the page. So the hydrogen will end up on a wedge. The hydrogen started behind the page, but when the bromine attacked from behind the page, it pushed the hydrogen in front of the page. So the hydrogen ends up on a wedge. I hope you can see now why this is considered an inversion. You can clearly see how the geometry of the hydrogen is getting inverted. The hydrogen is getting pushed, inverted from behind the page to in front of the page. An analogy that's often used for this is it's like an umbrella being blown inside out by the wind. You know, sometimes if you take your umbrella outside on a very windy day, the umbrella can get blown inside out. And that's kind of what's happening. It's like the umbrella gets inverted, and that's kind of what's happening here. The bromine is like a strong wind. The bromine is kind of like a strong wind coming in from behind the page here, and blowing the hydrogen, so to speak, from behind the page to in front of the page. So the hydrogen ends up inverted, and it's like the whole umbrella arrangement ended up inverted, so to speak. The hydrogen getting inverted from the dash to the wedge. So the geometry of this molecule has inverted, much like a strong wind can blow an umbrella inside out and invert the configuration of the umbrella, so to speak. Okay, so I think that drawing the position of the hydrogen in these 2 pictures might help to get us a better understanding of what the inversion of configuration means here. Now, that doesn't mean that you have to draw the hydrogen each time. In fact, maybe now I think I'll go ahead and erase those hydrogens. Normally, we're not going to bother to draw the hydrogens. Normally, we won't bother to draw the hydrogens, but it is good to know in the back of your mind. It's good to know in the back of your mind that even though we're not drawing the hydrogen, the configuration of the hydrogen is getting inverted in this SN2 reaction. Okay, so now we've learned this important rule about stereochemistry for a SN2 reaction. And now would be a good time to pause the video and memorize these two key rules. You should pause the video and memorize these two rules. All right, I hope you did that. Obviously, this rule is important because you'll probably be tested on SN2, inversion with SN2 on your exams. And it's also important, though, to know this rule because this is a rule that we're going to apply to other reactions later in the class as well. You'll have more opportunities to use this rule again later in the class. A nucleophile will attack from the side opposite to the leaving group. That explains the outcome for SN2, and it will also explain the outcome for some other reactions you'll study later in your course. All right, so we have introduced the basic ideas you need to understand stereochemistry for SN2 reactions. In the next video in this series, we'll move on to our next SN2 topic. Before we do that, let's do a brief review quiz. Please pause the video and answer, how many steps are there in an SN2 reaction? Here's the answer. There's one step in an SN2 reaction. Next question, please pause the video and answer, what exactly happens in that one step? Here's the answer. In that one step, the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. You should have this memorized. Why is it so important to have this memorized? Because as the class proceeds, you're going to learn many other reactions. You'll learn SN1 reactions, you'll learn E2 reactions, you'll learn E1 reactions, you'll learn many other reactions, and it's going to be really hard to avoid confusing all those reactions with each other. The only way to avoid confusing them is to memorize exactly what happens for each of the reactions. So we need to memorize exactly what happens for an SN2 reaction so that we don't end up confusing SN2 reactions with the many other reactions that we'll learn later in the class. Okay, now you can proceed to the next video in this series where we will be discussing our next SN2 topic.